Ready for a wild ride today? We're diving headfirst into the universe.
Yeah, tracing humanity's journey from a cozy, Earth-centered model to some seriously mind-bending theories, right?
Exactly. And to guide us on this expedition, we've got excerpts from, well, some heavy hitters.
Stephen Hawking's A Brief History of Time
Oh, a classic.
and Michio Kaku's The God Equation.
We're talking about the evolution of how we went from thinking the Earth was the center of everything to pondering black holes and hidden dimensions.
Yeah, it's like a detective story. Each new discovery is a clue, right? Either deepens the mystery or throws us for a loop.
I love that. Okay, so picture this. You're an astronomer in ancient Greece, and all you've got are your eyes and a whole lot of patience. What do you see?
You see the sun rising and setting, the stars, they're moving across the sky, and then there's the planets, right? They're seemingly doing their own thing, wandering back and forth.
And based on those observations, the model that made the most sense for over 1,000 years was what's known as the Ptolemaic system.
This model placed Earth at the center of the universe, with everything else revolving around us in a series of 8 celestial spheres.
8 spheres. Talk about cosmic real estate. But here's the thing. To make this model fit what they were actually seeing in the sky, astronomers had to add all these extra loops and epicycles to the planet's movements.
It got complicated, but it was the accepted model for centuries. And then along comes Copernicus in the 16th century.
Yeah, proposing this radical idea. What if we're not the center of attention? What if the sun is at the center and the Earth is just another planet orbiting it?
Talk about a paradigm shift.
Copernicus must have had some serious guts to challenge, like, the status quo like that.
He was worried about the backlash, actually.
Really?
Oh, yeah, he was concerned. So initially, he only circulated his heliocentric theory anonymously.
Wow. Talk about a strategic manuscript drop.
Yeah.
But even with a sun-centered model, there were still some cosmic puzzles to solve. And that brings us to a particularly intriguing head-scratcher, Olber's paradox.
Okay, imagine for a moment that the universe is infinite and unchanging, filled with an infinite number of stars. Now, if that were the case, then no matter where you looked in the night sky, your line of sight would run into a star.
Makes sense. Just like in a forest, eventually, you're going to run into a tree no matter which way you look.
Precisely. But here's the paradox. If the universe were truly infinite and static, the night sky wouldn't be dark at all,
It'd be blindingly bright, right?
ablaze with the light of countless stars.
So why isn't it? What are we missing?
This seemingly simple question, the darkness, it hinted at a universe that wasn't static and unchanging, but dynamic, evolving.
It's amazing how a simple observation can shake the foundation of our understanding.
Absolutely. And this is where Isaac Newton enters the scene, armed with his laws of motion and universal gravitation.
Newton, he was like the rock star physicist of his time. He explained why, objects fall to the ground, how planets move in their orbits, basically laid down the law for how gravity works.
And his laws were so precise that astronomers could do something incredible. They could predict the existence of a planet that had never been observed before Neptune.
Wait, hold on. You're telling me they found a planet using math? Tell me more.
Astronomers noticed that Uranus, discovered just a few decades earlier, wasn't quite behaving as Newton's laws predicted, its orbit a bit off. They thought, there must be another planet, as yet unseen, whose gravity is tugging on Uranus.
So they used Newton's equations to basically play cosmic detective. That's brilliant. Did they find it?
They did. Using nothing but math and the understanding of gravity, they pinpointed the location of this mystery planet, and lo and behold, Neptune.
That's like a cosmic magic trick. You can almost hear the collective gasp from the scientific community.
It was a stunning validation of Newton's theories, but as with all good detective stories, there was a twist. Even Newton's laws, as successful as they were, couldn't fully explain everything.
Oh no, there's a plot twist. Don't leave me hanging. What didn't fit?
The orbit of Mercury,
Mercury.
the closest planet to the Sun, had some peculiarities that Newton's laws couldn't quite account for. It was tiny, the discrepancy, but in physics, even the smallest anomalies.
Can point to the need for a bigger, bolder theory, right?
Exactly.
And that is where Einstein steps into the picture. Get ready for things to get really warped. So we've got Newton's laws, which work beautifully for most things, but then Mercury's orbit throws a wrench in the works. What happens next?
Enter Einstein, stage left, with his revolutionary theory of general relativity.
Okay.
Imagine this. You're in an elevator, and suddenly the cable snaps. You're plummeting.
Okay, worst nightmare fuel aside, I'm following. Go on.
As you're free falling, you'd feel weightless,
Yeah.
right? as if gravity has disappeared.
Right.
Einstein realized this feeling of weightlessness wasn't just a coincidence. It was a profound clue about the nature of gravity itself.
Wait, so you're saying my near-death experience in a plummeting elevator is the key to understanding gravity? My therapist is going to love this.
In a way, yes. Einstein called this his happiest thought. The realization that gravity and acceleration are two sides of the same coin. What we experience as gravity is actually the curvature of space-time caused by massive objects.
Okay, stop right there. Curvature of space-time. That's where I need a little help visualizing things.
Think of it like this. Imagine a bowling ball placed on a trampoline.
Right.
The ball creates a dip, a curvature, in the fabric of the trampoline.
Right, so any other objects on the trampoline would roll towards the bowling ball.
Exactly. Now replace the bowling ball with a massive object like the sun and the trampoline with space-time itself. Instead of rolling, planets are moving through this warped space-time, following the curves created by massive objects.
So gravity isn't so much a force pulling things together. It's more like massive objects are creating a cosmic slope that everything else slides down. My mind is officially blown.
It is a pretty radical way of thinking about gravity. And guess what?
What?
Einstein's theory perfectly accounted for that weirdness in Mercury's orbit.
So Einstein 1, Newton 0.
Not exactly. Newton's laws are still incredibly accurate for, most everyday purposes. Einstein's theory just provided a more complete and nuanced understanding of gravity, especially in extreme cases like the orbit of Mercury. But remember, we're not just talking about planets here.
Right.
This new understanding of gravity has implications for everything we know about the universe, from the Big Bang to black holes.
Okay, I'm officially buckling up for this cosmic ride. But before we get ahead of ourselves, we need to zoom in from the vastness of space to the incredibly tiny realm of atoms.
And the even tinier particles within them.
The quantum world.
Yes.
Hold on to your hats, folks, because things are about to get really weird.
It all started with the mystery of the sun's energy.
Okay.
Scientists knew it couldn't just be burning like a fire. It would have run out of fuel long ago. The answer, it turns out, lies in the bizarre world of quantum mechanics.
Okay, I'm intrigued. How does quantum mechanics explain the sun's seemingly endless energy supply?
It all comes down to nuclear fusion. Under the immense pressure and heat at the sun's core, hydrogen atoms are smashed together with such force that they fuse to form helium.
Wow.
And this process releases a tremendous amount of energy. It's like a cosmic power plant running on emission.
So that famous equation isn't just a theoretical concept, it's actually powering the sun.
Absolutely. But to understand fusion, we have to delve into the even weirder world of atoms and the particles that make them up, which means taking a trip into the quantum realm, where things aren't always as they seem.
Okay, I'm ready for the quantum deep dive.
Right.
What's the first rule of Quantum Club?
That things don't always make sense. One of the foundational concepts of quantum mechanics is this idea of quantization.
Okay.
That energy at the subatomic level comes in these discrete packets, or quanta, like a vending machine that only accepts certain coins.
So instead of energy being a smooth, continuous flow, it's more like a series of tiny bursts.
Exactly. And this realization led to another mind-bending discovery. Light itself can act as both a wave and a particle. It's called wave-particle duality. It's one of the most counterintuitive ideas in all of physics.
So light is both a wave, like a ripple in a pond, and a particle, like a tiny billiard ball. How is that even possible?
That's the beauty and the headache of quantum mechanics. Light, it seems, doesn't fit neatly into our everyday categories. Depending on how you observe it, it can behave like either one.
Okay, I'm starting to see why they call it quantum weirdness. Is there any way to wrap our heads around this? Or do we just have to accept that the universe is stranger than we can imagine?
It definitely takes some getting used to. Perhaps the most famous illustration of quantum weirdness is the thought experiment known as Schrödinger's cat.
Oh yeah, I've heard of that one. It involved a cat in a box, right?
Ugh.
But the details are a little fuzzy.
Imagine a cat sealed inside a box with a device that has a 50-50 chance of releasing a deadly poison. According to quantum mechanics, until we open the box, the cat exists in a superposition, a state of being both dead and alive at the same time.
Wait, so it's like the cat is in a quantum limbo, neither alive nor dead until we peek inside. That's just messed up.
It sounds crazy, but that's the essence of superposition. It's not that the cat is either dead or alive and we just don't know which. It's that the cat's fate is literally undefined until the active observation forces it to collapse into one state or the other.
This is blowing my mind. So are you saying that our Observation, our act of looking, determines reality.
In the quantum world, yes. It suggests that the observer plays a fundamental role in shaping reality, that the act of measurement can actually influence the outcome.
Wow, that's giving me a whole new perspective on the phrase observer effect. So this quantum craziness, does it apply to everything in the universe?
To a large extent, yes. These bizarre rules of the quantum world, as perplexing as they might seem, have been incredibly successful in explaining a wide range of phenomena. And they led to the development of the Standard Model, which is our best current theory for understanding the subatomic world.
So the Standard Model is like the ultimate physics cheat sheet. Tell me more.
You could think of it that way. It's a framework that describes the fundamental particles and forces that make up everything in the universe. Quarks, leptons, bosons, the whole gang.
It's like the periodic table, but instead of elements, we've got these exotic subatomic particles.
Exactly. And the Standard Model has been incredibly successful in explaining how these particles interact and combine to form everything we see around us.
That's incredible. So we've got the Standard Model to explain the tiny stuff and Einstein's theories to explain the really big stuff. Are we done? Have we finally cracked the code of the universe?
Not so fast. As with all good scientific endeavors, every answer seems to lead to more questions. And there's one glaring omission in our current understanding, one force that stubbornly refuses to fit neatly into the picture.
Don't tell me gravity.
You got it. The Standard Model, as successful as it is, doesn't include gravity. We still haven't figured out how to reconcile the very big with the very small to create a theory that encompasses both the vastness of the cosmos and the weirdness of the quantum world.
So even with all our progress, the universe is still holding on to some of its secrets. I have a feeling things are about to get even weirder as we explore those mysteries in Part 3. It feels like we've already traveled millions of light years intellectually from those ancient models of the cosmos to, well, the mind-bending world of quantum mechanics.
And it is mind-bending.
Are you ready to venture even further into the universe's weirdest corners?
And I do mean weird. We're grappling with concepts so extreme, so mind-boggling, they even make Stephen Hawking and Michio Kaku scratch their heads.
Okay, bring it on. I've got my thinking cap on. Let's talk black holes. I mean, everyone's heard of them, but what are they really, besides cosmic monsters that gobble up everything in their path?
They're the ultimate cosmic sinkholes, regions of space-time where gravity is so strong that nothing, not even light, can escape. Imagine the densest object possible squeezed down to a single point. That's the singularity at the heart of a black hole.
Okay, that's giving me a serious case of the cosmic chills. It's like the ultimate cosmic vacuum cleaner. But I thought, if nothing can travel faster than light, then how does a black hole's gravity trap it?
That's where general relativity comes in. Remember how we were talking about massive objects warping space-time?
Right.
Well, black holes take this warping to the extreme. They create a gravitational well so deep that it effectively punches a hole in the fabric of space-time.
So it's not just that light gets sucked in. It's more like space-time itself is so distorted around a black hole that there's just no way out,
Right.
not even for light.
Exactly. It's like trying to swim upstream against an infinitely strong current. And that point of no return is called the event horizon. Once you cross that boundary,
That's it.
there's no coming back.
This is way scarier than any haunted house, but also incredibly fascinating. I know Stephen Hawking, he did some groundbreaking work on black holes. What did he discover?
Hawking showed that black holes aren't completely black after all.
Really?
They actually emit this faint radiation, now known as Hawking radiation, due to quantum effects near the event horizon. It's as if black holes slowly evaporate over time.
So even black holes can't hold on to everything forever. There's a glimmer of hope there.
But what about the stuff that falls into a black hole? Does it just poof, disappear?
That is one of the biggest mysteries in physics, the information paradox.
The information paradox.
You see, quantum mechanics suggests that information can never be truly destroyed, just scrambled.
But black holes seem to break that rule. What happens to the information contained within the objects they swallow? Does it vanish? Does it get plastered onto the event horizon like cosmic graffiti? It's a mystery that still keeps physicists up at night.
Okay, black holes are definitely weird, but in a way, they kind of make sense, at least in the context of general relativity. But now we're heading into a realm that makes black holes look like child's play.
String theory.
String theory. What is this mind-bending theory all about?
String theory attempts to answer the biggest question in physics. How can we unify all the fundamental forces of the universe into one grand theory? It's the Holy Grail of physics. And string theory suggests that the fundamental building blocks of the universe aren't point-like particles, but tiny, vibrating strings.
So everything, and I mean everything, is made of these little strings. Not the kind I use for my guitar, I'm guessing.
Much, much smaller. We're talking about strings so tiny that they're billions of times smaller than an atom's nucleus. Imagine the universe as a symphony, and these tiny strings are vibrating at different frequencies, creating all the particles and forces we observe.
So it's less like a guitar string and more like each particle is a different note on a cosmic symphony played on these infinitesimal strings. That's a trippy concert I'd love to attend. But what about those extra dimensions I keep hearing about?
Ah, yes, the extra dimensions. To make the math of string theory work, physicists propose that there are more than the 3 spatial dimensions we experience. These extra dimensions are curled up, hidden within the fabric of space-time, too small for us to see.
So our universe is like a slice of a much grander, multidimensional reality. My mind is officially in the twilight zone. But hold on, is there any actual proof for string theory? Or is it just, a beautiful mathematical idea?
That's the million-dollar question. String theory is incredibly elegant, mathematically compelling, but so far, there's no direct experimental evidence to confirm it. It's like having a beautiful map with no compass to guide us.
So where does that leave us? We've traveled through the vastness of space, explored the weirdness of the quantum realm, peered into the depths of black holes, even ventured into the strange realm of string theory. What have we learned?
We've learned that the universe is far stranger, far more wondrous, and far more mysterious than we could have ever imagined. Every answer we uncover seems to lead to more questions, more layers to peel back in our quest to understand the cosmos.
I love that. So it's not about finding all the answers, but about embracing the mystery, the sheer awe of it all.
Precisely. And that's the beauty of science. It's not about having all the answers, but about the thrill of the chase, the endless pursuit of knowledge.
Well, on that note, let's end this deep dive with a few of those tantalizing questions that keep cosmologists and now us pondering late into the night.
The big ones are always there. Is ours the only universe? Or are we just one bubble in a vast multiverse? And
Yeah.
what happened before the Big Bang? Did time even exist then?
And the biggest one for me, is there some grand unifying principle, a theory of everything that can tie it all together? Is the universe ultimately knowable?
Those are questions for the ages. But even if we never find all the answers, the journey itself is what's truly remarkable.
Absolutely. The universe is like this giant puzzle box, and we're just starting to glimpse the intricate patterns within. So the next time you look up at the night sky, remember, you're not just looking at stars, you're looking at the edge of what we know, the boundary between the known and the unknown. And that's a pretty incredible thought to end on, don't you think? Thanks for joining us on this incredible deep dive.